Welcome back to the details video about our Melexis MLX90363 Triaxis magnetometer. In the previous video, we developed a basic framework for an Arduino library to work with that thing based on C++ Union, and we implemented one opcode, so operation code, identifying the messages going back and forth between our Arduino and that magnetometer. And that was the no operation opcode. So basically doing nothing, but it worked fine for one fact. We actually received a message back that was obviously not a response to a no operation command. Card here, link in the description. So in this video we will of course implement more opcodes, and we will hopefully remedy that error and probably do some more housekeeping with the library, and if there's time we will actually implement some useful commands, that is reading out some magnetic data from that chip. We'll see. Anyway, enjoy! You already saw that opcode table in the previous video. It's part of the datasheet, link in the description. And as mentioned in the previous video, we implemented the MOSI, so from master to slave opcode, NOP, no operation, and also the MISO, so from slave to master, reply opcode, NOP. Yeah, the reply to a NOP is a NOP. But as mentioned in the intro, we received a message from the slave that was obviously not a NOP message. We didn't know the opcode or haven't implemented the opcode yet. And in that table here of the MISO messages, there are exactly, let's say, 3 candidates for that unknown opcode. And that would be it's simply an error frame, something is wrong, or our little chip has nothing to transmit. Yeah, that could also be it. Or our little chip just sent us back a ready message. First slave out message after power on reset, POR. So let's implement these 3. That should be really quick, and see if we can operate the whole thing without throwing an error. Before we implement the 3 new opcodes for messages from the slave to the master, so MISO messages, we should talk about a specific characteristic of SPI communication between a master and a slave. I have here time scale, okay, and each of these blocks is a single SPI transaction. So we know that in a single SPI transaction, we transfer a message of 8 bytes from the master to the slave and receive at the same time, byte for byte, an 8-byte message from the slave to the master. So in our very first SPI transaction, if we send over a MOSI message with the opcode NOP, what exactly is the slave replying to? Yeah, you see, here is obviously our problem. For the second SPI transaction, if we transfer a second opcode, the slave is replying to the first opcode we sent in the first SPI transaction. And of course, in the third SPI transaction, the slave is replying to the opcode of the second SPI transaction while we are transmitting a new third opcode. Or in general, if we transmitting in one SPI transaction the nth opcode, the slave is replying to the nth minus 1 opcode. So yeah, when we first really power up the whole system, what is the reply to our first opcode, which was always a knob in all cases in the previous video, but what exactly is he replying to? We don't know. That is, yeah, we will find out in a second. I didn't realize that before, but the ready error and NTT, so nothing to transmit messages, are also handled in the datasheet in a single chapter. So methinks we're on the right path here. Let's start with the ready MISO message. That is, we have here the opcode hexadecimal to C. And here, of course, the marker is 1 for other message, and we have the CRC. Yeah, it's the same for all the other messages. And then we have in byte 0 the hardware version, in byte 1 the firmware version, and that's it. And it says here, after power on reset, the first MISO message is a ready message. And remember, in the last video, I only could reproduce the error when I freshly, that is, plugged in my thingy here. So right after power on. So yeah, that's probably the message we will be getting. But anyway, let's do the other messages too. And the next MISO message would be the error message with, in these 6 bits here, the opcode hexadecimal 3D. And CRC, yeah, again, it's always the same. And then we have here in byte 0 an 8-bit, so 1 byte error code. Though there are only 4 error codes here. So 1 would be an incorrect bit count, 2 would be an incorrect CRC. Yeah, I handle that also on the other way, on the master side in the library already. 3 is an answer equals NTT message. 2 reasons, answer timeout or answer not ready. Which is interesting because there's also that NTT message. Anyway, 4, opcode not valid. Remember, I do the same test on the master side in our library. Finally, we have the nothing to transmit message here with the opcode hexadecimal 3E. Yeah, 1 for other message, the CRC, and then some random bit pattern here, which I really don't care about. I think it will be enough if we just verify that it's the right opcode, the right marker, and the CRC is correct. However, note these comments here for the NTT message. In most of timing violations, the slave answers with an NTT message. Yeah, it says here in most. I guess in other timing violations, which are not most, it will answer with an error frame and just gives you here error code 3, answer NTT message, answer timeout or answer not ready. It also says here, in normal operation, NTT messages are not supposed to be observed. The master is supposed to respect the protocol timings defined. Something which we don't do right now. So yeah, there's even more stuff to implement in future videos. But anyway, let's have a look now how we implement that stuff. It should be quite straightforward. The implementation was not as quite straightforward as I thought. Anyway, let's go over first the changes and additions to the .h file of the class. We are in the public part, and of course I introduced a new enum class error code with the error codes for bit count error, CRC error, entity error, and opcode error in the error messages. Please note the previously private enum classes marker and MISO opcode are now public too. Reason being, now that our class can process different messages, our other code must be able to determine through some class methods which message has been received from the slave. So these classes marker and MISO opcode now being public. Also, of course, I extended MISO opcode here with our new opcodes ready, error, and NTT. We have two new public methods, last marker and last MISO opcodes. We talk about the details when we have a look at the CPP file in a second. Three more public methods. Last ready hardware version, last ready firmware version, and finally last error code. Again, details when we look at the CPP file. We're in the private part of the class now, and I extended the typedef union MISO message, adding a member ready as a struct ready for the ready messages, delivering us the hardware version byte and the firmware version byte from ready messages, as well as a struct error for the error messages, which just contains here also a byte, the error code enum we defined above, error code. Finally, we have a new private method, valid marker opcode. Details, again, in a second when we look at the CPP file. Which we'll do right now. So here is the implementation of our first new public method, last marker, which of course returns the marker contained in the last MISO message received from the slave. We use the usual technique to extract that. So we have our MISO message union, we select the member other, and within that member we return the marker opcode, binary ended with that bit mask here, just delivering us the two most significant bits. We cast that to the inner marker and return it. Analog here, the implementation of last MISO opcode, which returns, of course, the MISO opcode contained in the last MISO message we received from our slave. Same technique here, MISO message, other marker opcode, but this time we binary end that with a bit mask that only gives us the 6 least significant bits, and I probably should define some constants for that so it's a little bit more readable. We cast that to the enum MISO opcode and return it. Then we have here the last ready hardware version, returning, of course, the hardware version contained in the last MISO ready message. Nothing new here, it's really primitive. Analog here, the last ready firmware version, so trivial. And of course we had that last error code, which returns the error code contained in the last error MISO message from our slave. So we just return here MISO message error code. And I probably should cast that into, because we are returning here an enum. So to make that formally correct, we should do a nice cast here. Yeah, just so it looks nice. That was a new private method here, valid marker opcode, which gets as an argument the marker opcode byte from a MISO message. And internally we maintain here just a list as constant expression array of all the MISO opcodes we already know. We have here for a loop a little variable, and then we go through our whole array and we just check if that marker opcode we got here is contained in the array. We are assuming at the moment, that we always have a marker other in the two most significant bits of the marker opcode byte. And if that's the case, that is, we know what kind of message we got from the slave, we return true. Otherwise, we return false. And we use that new private method inside our private send method. And we do that down here. So previously, we just had to check for one valid opcode marker combination because we have only implemented one message. But now we are using that new method here to determine if we know the type of message the slave has returned, and if that is not the case, then our last library error, as before, is a library error opcode and return false. So yeah, I can delete that command now. The only changes in our sketch itself are here in the loop, and not here in the error handling, but here in the else part, where I previously just printed out unconditionally the content of a NOP message, because we were only able to receive NOP messages. And that is now extended here with a switch that uses the last MISO opcode method we received from the slave. And then I do a case and I print out here, for example, the information contained in a NOP and the information contained in a ready message. So the hardware version and the firmware version. I also print out the error contained in an error message. And here I do a little bit secondary switcherooing just to give you here not just the numbers, but yeah, the name of the 4 errors that chip knows within at least the error messages. That's what we know so far. And yeah, for the nothing to transmit method, I just print out nothing to transmit because it doesn't contain any data. And that's all. Now let's test that code. I have, yeah, still disconnected here my little breadboard, and I plug it in now. Boom, 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 boom. And we activate the serial monitor, and let's see. Oh, that's interesting. Let's stop that. So we got an error message back with a bit count error. Ah, that's eerie, but not what I expected. I would have expected a ready message or a message like nothing to transmit, but not an error message with a bit count. Let's try that again. Disconnected, plugging in, and opening the serial monitor. Ah, okay. That's better. Auto scroll off. Now we get an error message with the error code nothing to transmit. Okay, I can understand that because, yeah, we sent our first NOP command, okay, but our little chip hasn't received any command before after power up. So it responds with an error code nothing to transmit. Makes much more sense. I guess the power up timing the first time around was a little bit off, something weird going on our SPI bus, and so it received a partial SPI message with yeah, not enough bits or something. Okay, but still, the fact that we can in our little system receive different error codes after power up is not optimal. Especially, let me close the serial monitor here and just reopen it. And then we get absolutely no error message. So yeah, there is some room for improvement. And we can improve that situation by setting our little chip into a defined state after we execute the begin of our library. And for that, we can use a reboot MOSI message. Or so you would think. And in my experience, it would work with basically every other chip I ever came about. However, there are some constraints when you can actually reboot an MLX90363. And in the datasheet it says here, it's a valid command in the following 3 cases after an EEPROM write. Yeah, we don't do that. In failsafe mode, meaning something went wrong inside the little chip and it went in failsafe mode. Or in standby mode, you can put the chip into a standby. In normal mode, so normal operation, Reboot reports wrong opcode. So we would get an error message with a wrong opcode or something. Okay, the reboot message is quite easy. Yeah, we have other message marker here, 11. And then we have here the 6-bit opcode, which is hexadecimal to F. Besides all, these constraints, let's just implement that reboot and put it into our begin method and see what happens. In the public part of our method in the .h file, I changed the begin from being a void to a method returning a bool. And of course, we have that new public method sendReboot. In the private part, we added a new member reboot with the value, of course, hexadecimal 2F to our enum class MOSI opcode. And we also extended the typedef union MOSI message by adding a member reboot, which is, of course, a struct reboot containing just, 6 unused bytes. These variables are really just here in the struct, so we can initialize everything nicely to 0, which is recommended. In the CPP file, I modified our begin method, which is, I already mentioned it, a bool. So after our pin mode and digital write, I have now a delay of 1 millisecond, just letting everything settle down. Then we will use the new sendReboot, which might fail, so we have here a Boolean success that is returned. Then we wait 25 milliseconds. There is a whole timing table in the datasheet, and it tells you that the time to reboot on 5-volt operations is 20 milliseconds, and on a 3.3 volt operation it's 23.5 milliseconds. So I wait, to be on the safe side, 25 milliseconds here, and then I return if our reboot was successful or not. Our new sendReboot method is trivial, works exactly like the sendNob we already implemented. I have a local variable MOSI message here, and then I first initialize the reboot member of our union, all the unused stuff to 0, and finally the all member, the marker opcode to, the marker other, binary odd with the MOSI opcode for reboot. And then I return the result of our send MOSI message. That's it for the CPP file. In the sketch itself, within the setup function, I now handle a possible failure of our begin method, and if such a failure occurred, so we return false here, I use that new function handle MLX90363 last library error, which gets our MLX90363 object passed and a string indicating where the error occurred. We'll have a look at that function in a second. Within the loop, I no longer here do my own handling of library errors. Instead, I'm using that new function here. And that new function will contain basically that switch statement and a wee bit more. So we can delete that now. And here's that new function. As mentioned, it gets an MLX90363 object passed, to be more specific, just the reference to the object, and that string where we can indicate where the error happened. Some serial print here, nothing fancy, library error during string, and then colon, and then follows the switch statement we already saw and have used in the past. Let's test that code. I freshly connect my breadboard to the USB. And I open the serial monitor and we'll see. Let's stop the scrolling. So we had an error message with the error code OpCode. Exactly what we expected. But that was on a new power up. Let's close that serial monitor and reopen it again. Okay. So without really cutting the power, just resetting our Arduino, we get, sorry, auto scroll off, the same result. So at least we are consistent now during the startup of our script. But we still haven't really initialized our little chip with a reboot. So there's some more work to do. So back to the drawing board. We already know that reboot is only a valid command after an EEPROM write, which we don't do currently. When the chip goes into failsafe mode, then something else is really wrong, and in standby mode. So let's implement the standby MOSI message and the associated standby acknowledge MISO message. The standby MOSI message is a primitive thing in itself, like the reboot message. So yeah, just the CRC byte and here the marker opcode byte with 11, marker for other messages, and then a 6-bit opcode hexadecimal 31. However, the lights just went out. I already mentioned in a previous video that I have problems with my studio lighting. So yeah, this is emergency lights on, but at least we can continue and we will handle the probably thermal problem of my studio lighting in another video. Anyway, where was I? Yeah. Standby is a valid command only after a NOP or a diagnostic details MOSI message. So yeah, seems we can't really win, can we now? And of course, the sensor answers to standby is a standby acknowledge. We've already implemented the NOP, so that's good. However, this dependency on the previous send MOSI message doesn't stop here. It affects basically all MOSI messages. And there is here a chapter 1310 in the datasheet, timing specifications per opcode. We're not really interested in that. And next allowed messages. So yeah, for get 1, get 2, get 3, we haven't implemented that. after each of these MOSI messages, you can do a follow-up NOP. So we're golden there. That table continues on the next page, and we see here, okay, after memory read, MOP is okay. EE write, yeah, we cannot use a NOP there, but currently we don't do EE writes, so it should be okay. Then after an EE challenge answer, whatever that is, NOP is allowed. EE read challenge, we're not reading the EEPROM at the moment. NOP is not allowed. After a NOP, you can do all commands that includes a NOP. After a diagnostic detail, we can do all commands including a NOP. After an oscillator counter start, not implemented yet, we cannot do a NOP, but after oscillator counter stop, we can do a NOP again. After a reboot, we can do NOPs. And after a standby, all commands are valid, we can also do a NOP. By the way, C startup sequence doesn't yield much information in regards to what commands you can use next, but NOP is one of them. But there was a second message that was allowed before a standby, and that was a diag details. And I won't bore you here reading that all, but on the first page we can use the diag details in exactly the same situations we can use the NOP. And that initially here, at least for the memory read, continues, but then EE write, yeah, it still continues. We can use a NOP or diag detail after EE write. But then here, the EE challenge answer, we can use a NOP here, but not a diag detail. EE read challenge, same for the NOP, we can't use either. NOP challenge, all commands, yeah, including the diag. I should make that also green, sorry about that. Then oscillator stop, start, we can't use either. Then oscillator counter stop, we can use the NOP, but not the diag detail. And then reboot and standby, it's the same. But in the end, there are 3 commands, after which we can't use a NOP, and there are 5 commands after we can't use a diag detail. So I would go with the with the NOP in that case, and we for now just ignore the whole EE write stuff where we can't use a NOP and the oscillator counter start where we can't use a NOP. Just to recap and visualize that craziness. So in order to be able to issue a reboot MOSI message, we must be first either have written the EEPROM, went into standby mode, or have ended up somehow in failsafe mode. To get into standby mode, we must beforehand issued a NOP MOSI message or a diagnostic details MOSI message. But we are not allowed to issue a NOP MOSI message if we beforehand did an EE write, EE read challenge, or oscillator counter start MOSI message. And we're not allowed to issue a diagnostic details MOSI message if we, issued before these 3 MOSI messages, plus the EE challenge answer and oscillator counter stop MOSI message. Anyway, we will now try to implement that pass here. So issue a NOP, go into standby, and then do a reboot. One more time, additions / changes to the code. And by the way, it's 31.1 degrees Celsius in here by now, so no wonder the electronic transformer of my studio lighting overheated. Anyway, we are of course in the .h file, and in the public part of our class definition we added a new member standby hexadecimal 32 to our MISO opcode enum. Of course, we have a new public method, bool send standby. In the private part of our class, we extended the MOSI opcode also by a member standby, which is hexadecimal 3.1. And of course, our typedef union MOSI message has also been extended by a member standby, which is a struct standby, which just contains 6 unused bytes, like the reboot. They are basically the same, so I have to think about another mechanism because this is a repeat and I don't like it. And that's it for the .h file. We are already in the CPP file, and here is the implementation of the method send standby. So yeah, it's exactly the same for send reboot. Just here our MOSI message, initializing the unused stuff to 0, and then setting our all marker opcode to marker other, and then MOSI opcode now standby, and then return the send MOSI message. And I haven't forgot to add our new MISO opcode standby to the list of valid MISO opcodes in our private method valid marker opcode. You have to maintain it at 2 places. That's not very nice, but I don't have another solution for that for now. With all that new stuff, I was able to revamp our public begin method. So the first few lines here are still the same. Then I do a send knob to get into kind of a defined state. I wait here 136 milliseconds. That's the time you have to wait after sending a knob command before you can send another command to the slave. It's defined as T short in the data sheet, so 120 microseconds for 5-volt operations and 135 microseconds for 3.3-volt operations. Then I do a send standby, and I want that to succeed, otherwise I return a false. And then I check if the last MISO message I received was actually a knob, because beforehand we sent a knob. Yeah, so we are syncing up now and checking, yeah, are we in sync, the master and the slave? If that's not the case, I throw a last library error, a library error opcode. Yeah, maybe I should use a new error code here, but I was too lazy. And return false. Otherwise, if everything was fine, I do another delay microseconds of 136 microseconds. You have also to wait after standby the same amount of time, T short, before issuing the next command to the slave. And the rest here, we saw that before, if not send reboot, return false. But now I also check if the reboot succeeded, if my last MISO message was basically the standby acknowledgement, because beforehand, yeah, we sent a standby. So if we successfully put the thing into the standby, we should receive, when sending now the reboot message over, back the standby acknowledgement from the slave. Yeah, same if that doesn't work out for us. Library error opcode, return false. And then we already saw that I wait the 25 milliseconds T reboot before I return true, assuming that we this time successfully and reliably initialized our little chip. And that's it. No changes to the sketch. So let's have a look at the results. Same game. I have here my breadboard unplugged and I'm plugging it in. And now we open the serial monitor and we see, wonderful. So We already sent in the sketch the first knob, and we receive from the first knob the ready message, which we would expect after a reboot. So ready hardware version 17 and ready firmware version 40. Great. But what happens if I now just don't power cycle, but just close the serial monitor and open it again, just resetting the Arduino, and again. Something useful, no error, repeatable. That's what we wanted. That's it for today. Yeah, we will defer the reading out of actual magnetic data from our chip here to the next installment, because initializing that thing in a reliable and repeatable way was a little bit more effort than I expected. But in the end, we prevailed. See you next time. Bye.